Hello there, everyone, and welcome to another edition of Starry Skies, the magazine programme that tells you all about what to see in the night sky in this month of November. I'm Mark Hardacre.
And I'm Steve Tonkin.
And we've got the clocks gone back now.
Yay.
Which means, of course, the night sky is a bit more accessible. And so it's getting dark about, 6 o'clock-ish?
Oh, more like 7 at the moment, but it's proper dark. Yeah. But no, it could be good. It could be good.
Yeah, we just need no clouds anymore. That's what we need now. This month, what we thought we'd do, a little bit different, we're going to talk about stars and their colours. You know, normally we do the planets and the constellations and constellation of the month. Well, we thought we'd ring the changes this time, right?
Absolutely, because colour tells you a heck of a lot about stars, which is, and most people just think stars are just they're all just white. They're not. Have a look.
That's right.
And especially, if you use something like binoculars to have a look at them, just defocus them slightly and it really brings out the colour.
That's it. And like you say, some are bluish white. That's what we think a normal star is, right?
Yeah.
And then a warm yellow, and even a few that are properly red.
Oh,
right?
yeah.
So there's no green, and I don't think there's any purple. But
there are no green stars, and purple stars no, because it's because of how the colour is generated that we won't actually see purple.
So when we're talking about star's colour, Steve, what we're really talking about is its temperature, right?
Indeed.
Like a piece of metal, if you put a horseshoe in the fire, it can be red hot and then yellow and orange and white. That's the same as the stars?
Absolutely. So as it moves along the rainbow from red to blue, we're just about getting there, yeah.
So the cooler stars,
they're reddish,
right?
Oh, there's a really, really nice. It's one of my favourite star names, and we can see it in about a month's time. It's a star in Lupus.
Uh-huh.
Its designation is RU. Right. So it's RU Lupi.
RU Lupi. And that's a really cool star?
It's a really cool star. It's what's called a carbon star.
Right.
And it's remarkably red.
Right.
It's like this little drop of blood in the sky.
So what temperature would that be then, roughly?
You're talking about, sort of 3,000 degrees Celsius-ish. Right. So still pretty blooming warm, but yeah.
But in comparison. Whereas a medium hot star, I guess that would be like our sun then?
Our sun, yeah. Our sun's a sort of fairly, I suppose, bog standard average star. It's about 10% of stars are like our sun, and it's known as a yellow dwarf.
Yeah.
And it's even though we paint it yellow in pictures and stuff like that, but actually, now you shouldn't stare at the sun, and definitely not with optical instruments. But if you actually look at it, it's actually not yellow when it's high in the sky. It looks white.
It's white. So yellowy white is the sun, and that's a temperature of about 5,500 degrees centigrade, roughly.
Something.
But what about the blazing hot ones then? What are they?
Oh, they get up to about 20,000 degrees, and those are the ones that are distinctly blue. In astronomers' term, we say those ones are what's called an O spectrum.
Right. That's a super blue, white hot star, 20,000 degrees maybe.
Youch.
So if we were looking in a November evening now, mid-November evening, and we were looking to the east, we'd probably see Orion, and many of us could recognise Orion.
Yeah.
So there's a couple of stars there that really illustrate these temperatures, right?
Absolutely. I mean, you've got... So as you're looking at it, the left-hand shoulder of Orion is a star called Betelgeuse, or Betelgeuse if you want. Yeah. Come on, nobody cares if you call it Betelgeuse. And that is distinctly orangey red. And there's another one you can find as well. Orion's belt is, I think everybody recognises it. If you follow the line of the belt up to the right, that leads to another reddish star, which is called Aldebaran.
And those two stars are cool and old. Right?
Oh, yeah. They're what's called red giants.
Right.
And they're coming towards the end of their life. And, yeah. Well, and when we say that, this could be another million years before they come to the end of their life. But they're definitely older.
And there was talk about Betelgeuse exploding in a supernova at some time, but not this year, right?
No, it might have happened already, of course. We wouldn't know for about 650 years, because that's how long light takes to get from it to us. The universe is big. Yeah.
So if we were looking at... So Betelgeuse is in the top left, right,
as
we
you're
look at it.
Yeah.
Top right, then... Bottom right.
Top right is Bellatrix.
And bottom
right
is Rigel. And that is an extremely young, massive, and very hot star, isn't it? That's a blue. So the contrast between those is extreme, right? One's very old and red, and one's new and white hot.
Yeah. And I think the thing we have to remember about all these things when we're looking at them is that it looks like they're all the same distance away, but actually they're not. What you're looking at in the sky is in 3 dimensions.
Right.
But it's sort of like it seems like it's painted on the celestial sphere. The other really nice, hot, white, bluey white stars in Orion are around the belt.
Yeah.
Easier to see with binoculars. I mean, there's the belt stars, but there's a cluster around the belt. I call it the cluster that every amateur astronomer has seen, and hardly any of them know, called Collinder 70. And you look at it, you've got hundreds there in binoculars, 10 by 50 or 8 by 42 binoculars, easy. Hundreds of stars in this cluster of stars. They're new, young stars, and those are also bluey white, most of them.
And to find it, all you have to do is point your binoculars at the 3 belt stars of Orion.
Absolutely.
And the field of view will be filled with these new, young stars.
And with anything in binoculars, if you're looking at the sky, if what you think you've aimed at is not in the field of view, go upwards, because you're almost certainly too low.
Yes, that's true. Yeah. So this temperature thing again, let's go back to the temperature.
Yeah.
It's not only that determines its colour, but it's also a clue to the star's life story, right?
Oh, yeah.
So hot blue stars, what's happening there? They're fuel, they're gobbling it down?
They're young, they're burning up hydrogen.
So they're like teenagers, right?
Oh yeah. And they're living life to the absolute full.
But they're going to go in a big bang eventually because they're going to use up their fuel, right?
Well, the big one, the rate at which a star uses its fuel depends on its size.
Right, its mass.
On its mass. Because you've got 2 things working against each other in a star. You've got the mass, which is gravity, so trying to collapse it all in, so pushing it in, or pulling it in, whichever way you want to think about it, and the nuclear reactions which have been set off, this nuclear fusion is pushing outwards, so you've got this dynamic balance of nuclear fusion pushing outwards and gravity pulling everything inwards. And the bigger the star is, the more gravity it's going to have, so the faster it's going to live its life.
So that means Rigel doesn't have too long to live. It's burning its fuel at a rapid rate of knots. It's going to turn into a supergiant and then a big bang, probably.
Oh yeah, we hope so.
Yeah. Whereas our sun, are we stable? Are we going to have the sun around for a bit?
Only for about another 4,000 million years.
Oh, that's all right. I was going to apply for my pension a bit earlier.
Yeah,
anyway.
No need to do that.
But just when I look at stars, though, they twinkle and change their colour. So is that part of the same story, or is that something else?
No, that's something completely different.
What's that then?
Okay. You notice it most with a bright star, and again, time of year for another bright star is if you follow Orion's belt stars down to the left, it comes to the brightest star in the night sky, which is Sirius.
Right.
And when that's low on the horizon, it tends to flash different colours as it twinkles. Right. And that is because there's little bits of the atmosphere act like prisms and disperse the light. So, but it's all very, very dynamic, the atmosphere, because it's moving. So sometimes you'll get red, sometimes and you will even get greens out of that one, because it's like splitting up light into a spectrum. And a little trick you can do, if it's really doing that, just with a mobile phone camera, point at that, and as you take the shot, move the camera, and the streak you'll get will be a streak of different colours.
Right.
Joseph's
for a star low down.
For a star low down near the horizon. A bright star low down on the horizon. You could call it Joseph's Technicolor Dream Star.
So, but if we were in space, so if you're looking from the ISS, the International Space Station, none of the stars would twinkle. They'd all have their own colour. Is that right?
No twinkle at all.
No twinkle in space.
Twinkle is atmosphere.
What about on the moon?
Unless your eye was right on the surface, and probably even not there, because the moon, believe it or not, does have an atmosphere, but it's only about 3 centimetres detectable.
Right.
But no, that wouldn't be. There wouldn't be enough there to be able to distort the light.
So twinkling stars is an artifact of the atmosphere on Earth.
Yeah.
The real colour is due to their coolness, their temperature, their size, and so on.
Absolutely.
So then, what about how do we study that starlight in detail? The light it's been on its way for centuries, maybe, and it arrives at our eyes and our instruments. How do we analyze that light? What do we use to analyze it?
Well, we use something. We intentionally split the starlight into its spectrum.
Oh, like a prism?
Like a prism, or a thing called a diffraction grating.
Right, yeah.
So you intentionally do what the atmosphere is doing to those lower stars,
right.
and you do it in a very, very stable way. So you spread the light out into a rainbow.
Yep.
Spectrum comes from, spectra, ghost is what they...
Okay, and with that spread out light, then we can tell what's in the star?
Yes.
Its chemical composition?
You can. You'll get dark lines in it and bright lines in it.
Right, okay.
Those are called spectral lines. The dark ones are called absorption. Bright ones are called emission lines. And it's fireworks time of year. It's exactly the same reason, really, that different fireworks have different colours.
Okay.
The different elements in there all have their own what's called spectral signature.
Right.
And it's a few lines, or sometimes lots of lines, and that enables us to identify what the chemical composition of the star is, which is amazing. You've got something where light's travelled maybe 1,000 years to get here, and you know what it's made of.
It's amazing, isn't it? So by splitting it up, we can figure out what is in the star, which elements are there, what its temperature is, because we know from its colour, overall colour, what it is. We can figure out how fast it's moving towards us or away
from us. You can figure out how fast it's rotating.
Yep. And even its age, roughly.
Yep.
So the bigger the star, the less likely it is to be an old star, so on. So it is really amazing that we can detect so much just from the light of the star without being there. And
absolutely, yeah. It's astonishing. I mean, it's where real, professional astronomy is all done with spectroscopy.
Absolutely. So at the heart of these stars, all of them, what's happening? We got hydrogen there. That's the main gas in the universe, and that's been turned into helium, right?
Yeah.
And what happens when we turn hydrogen to helium?
Well, what you find is that if you take the mass of the hydrogen that's combining and then the mass of the helium that's resulting, there's a very, very tiny difference. There's a mass deficit in the helium, and that mass has been turned to energy.
And that's light.
And that's
heat.
energy it actually takes millions of years to get from the core of the sun to the edge of the sun.
Right.
And then once it's got to the edge of the sun, it takes, after that million years travel, or however long it is, a mere 8 minutes and 19 seconds, and it hits us on Earth.
But what happens? So this can't go on forever. What happens when a massive blue star, for instance, runs out of hydrogen? Does it just turn off like a switch, or what happens then?
Well, in a sense, it starts to turn off because, as we said, you've got this dynamic balance between the nuclear pressure outwards and gravity inwards.
Yeah.
So that stops. Gravity wins, so it compresses it, heats it up, and that can start a new set of reactions. So you get then the things that we know about. The elements people are aware of: oxygen, nitrogen, carbon, all of those things being formed
in the middle of the sun.
In the middle of the sun,
right.
Or it depends on the size of the star. In some stars, it happens throughout the star.
Right. And then what happens at the end of all this? Does it go on forever?
Well, it depends on the size of the star.
Right.
Well, it won't go on forever. But if you take a massive star, at the end of it, we said massive star, everything happens much quicker.
Yeah.
Then that goes. And then you're combining those things to make other things, and you get all the way up to iron.
Right.
And then you can't go any further.
Until the whole thing collapses into a supernova blast, and then even the iron is converted, isn't it, to the really heavy element?
Oh, yeah. So what happens is, you can imagine, the nuclear reaction just stopped. Okay. And what happens next takes place over minutes rather than everything could be going on for years. And so the whole thing starts collapsing in under gravity. And the core gets so hot it destroys itself. So you get this destructive thing which blasts material outwards at about the speed of light. But the stuff that was still coming in is coming in as close to the speed of light as well. And these two fronts hit each other, and bang, and it combines all these other elements, the stuff we really like gold and that. That's why they're so rare, because it's this rare event that makes them.
So they come from supernova. So this little wedding ring I have on my finger here, that gold and yours came from the middle of an exploding supernova. And all the atoms in me And you?
Everything except the hydrogen was made in a star.
Right. Isn't that amazing? That is really, truly amazing to think that we are all star stuff.
So, Mark, as they sung, around the hippie era in San Francisco, we are stardust, we are golden.
Yeah.
Or if you're not feeling that good about it, we're nuclear waste.
And at the centre, so when everything's died away, what we're left then is that little core, a small dense core, which we call a white dwarf, and that thing burns and fades slowly over really trillions of years.
Oh yeah, so if the sun will go to a white dwarf, but a massive star, anything about 8 times big, get a thing called a pulsar.
Yep. Which
is denser than a white dwarf. So you can imagine you've got something the mass of the sun, but about the size of Verwood.
Wow.
So it's incredibly dense, spinning thousands of times a second.
Yeah, because all that angular momentum from the rotating sun would compress into something the size of Verwood.
Yeah, so like a skater or somebody, you pull all the mass in if you want to rotate faster, spread it out if you want to rotate slower. And it's,
And all that material that was the sun, let's call it, that was blown out, is now blown out into space. Yeah. Is that like the building blocks for new suns?
Indeed,
and then new stars and
yeah.
solar systems?
Yeah, and you can see these things where it's happened. So you get things called planetary nebulae, which got nothing to do with planets whatsoever, just so they look like ghostly planets. Nebula just means a ghostly cloud thing. And so the planetary nebulas from a star like our sun, and the big ones, the much bigger ones, they give something called, it's the result of a supernova. It's what's left, so it's just called a supernova remnant.
Yeah.
And there was a supernova in 1054, which the Chinese astronomers studied, and they called it a guest star because this star arrived. It was really bright. It was visible for about 8 days during the day as well. And this is how bright the thing is. And then, like any good guest, it faded and left.
Leaving behind a tiny little patch, which you can see with your binoculars, just with a small telescope better. Yeah. And it was the first object in Mr. Messier, our friend Charles Messier, in his catalogue. That's M1. And it's a really super supernova remnant from when? 1054.
Supernova 1054.
That's the one, yeah. So again, just when you look, everything around you, just look around your room where you are now, everything that you see came from a star exploding or puffing its atmosphere out into space billions of years ago. And that is a startling piece of information.
And the information you can get from that is incredible. Okay, we're only seeing stars, as we know, we're only getting snapshots, on different stages of their lifetime. But if you imagine you're walking in a forest and you see an oak tree and it's got acorns on it, and you look on the ground, there's acorns on the ground, and you look, some of them are sprouted, and the sprouts have got oak leaves. From little things like that, these little snapshots, you can work out the life cycle of an oak tree. Yeah. And it's the same. By looking at stars at different stages of their life, we can work out the life cycle of stars.
Yeah. So this is not, again, this is the way science works.
Indeed.
We've put together a map, a time map, if you will, of stars' life, birth, death, and we believe now that this is correct. Of course, science is always changing, and if new evidence comes along, we change our theory always. But that is pretty much how we think stars are born, live, and eventually die. And it's fascinating, isn't it?
It is. It's wonderful. That's why we love this subject so much.
So that's a bit different this week, or this month, isn't it, to talk about stars. So let's have a little bit about the night sky in November. What we're going to see in November, Steve?
Well, we are going to see the summer, the winter Milky Way, which is actually very, very faint.
Yes,
because I think we're about 2/3 of the way out from the centre of the galaxy. Yeah. In the winter, we're looking out, so there's not so many stars along in that direction.
Still there, though. We can still see it on a dark night.
Oh, yeah.
Don't try and see it when the moon's out, though.
No, you won't see it. No chance.
And I think the full moon in November is on the day that this is going out, for the 5th of November, I think it's a full moon.
Oh, Guy Fawkes night.
Guy Fawkes night, yeah. So, and it will be in the constellation of Aries, which is just to the left of the great square of Pegasus, the flying horse, which you can see pretty much mid-sky, southeast to south, around 10 o'clock or 11 o'clock in
and you look below that,
Yes.
And what do we got below it, Mark?
We've got Saturn, right? And as we said last month, Saturn is in a particularly barren area of the sky right below the square of Pegasus. Relatively easy to find because there's nothing else there. But this month, during the month of November, the rings of Saturn will close up completely. So even with our big telescope at Knowlton, our 12-inch monster down there, the rings will actually disappear for a day or two as they appear to be edge-on as seen from the Earth. Only for a couple of days, and then they'll slowly start to open, and over the next 5 to 6 years, they'll fully open again. Yeah. And Saturn will get much brighter.
Yeah.
Because all that reflectivity from the rings. But right now, Saturn's about as dim as it can get.
Yep.
And not particularly good to see in binoculars and telescopes because the wow moment isn't there, is it?
No, but we'll get it back again. Don't worry.
We will.
Come to one of our stargazing events. We will show you.
Yeah, we will. So so Saturn is more or less due south during November. Let's turn our head towards the left and low in the northeast, and there around about 11 p.m. mid-November you'll see Jupiter.
Ah, the king of planets. Yeah, Zeus it was for the ancient Greeks.
So it was, and he's so bright, again, you can't miss him. Fourth brightest object in the sky, Sun, Moon, Venus, then Jupiter. And even with any old optical aid, you'll be able to see the 4 moons. We've talked about these 4 Galilean moons of Jupiter before, but you can really see them with a simple pair of binoculars, even what used to be called an opera glass. You remember opera glasses?
Opera glass, yes.
Yes.
Oh, a Galilean binoculars.
There you go.
But I've actually even seen them with, kids' toy binoculars with plastic lenses.
Ones,
horrible. I've even seen the 2 outer moons with that. Not at the same time, because they've only got one little sweet spot.
That's it. And, of course, you have to know that Steve Tonkin is well known in our group of astronomers as Dr. Binocular, because he writes a column in the Sky at Night magazine once a month about binocular objects, and it's a fascinating read. Go out and buy it from your local W.H. Smith's. Other shops are available, and you'll be able to get a list of nice objects to see every month in the sky with binoculars. So that's Steve Tonkin's Dr. Binocular spot in the Sky at Night.
And what a lot of clubs do, they actually use that also for telescopes for beginners.
Yeah, it's great. There's usually 5 or 6 objects to see.
6 objects.
Yeah.
Sometimes I choose really big ones which you're not going to see in telescopes.
Yeah.
But, usually it's something you can see in a telescope.
But definitely the moons of Jupiter, we should see them right the way from November all the way through to probably March or April next year before we lose Jupiter. So all the way through winter, you will not miss it. Jupiter is in the constellation of Gemini and will slowly, during the course of the year, move backwards and forwards and slide out of Gemini probably towards the middle of spring somewhere, March, April time. With a decent telescope, like the one, for instance, that we have at Knowlton, 12-inch telescope there, you can see the disk. You can easily see the several dark bands that surround Jupiter, made up of ammonia and other smelly gases that are horrible. And, of course, the famous red spot, which we call now the what? The little pink...
the not-so-great salmon pink spot.
Yes.
The moderate.
Yes, it's a huge spot in the atmosphere, or storm in the atmosphere of Jupiter, which has been there for at least 300 years. Yeah.
How big is it in relation to what things we know?
Yeah, I think, if I recall right, from Patrick Moore's little book, I think you can put 12 Earths alongside. I think it's 12 times the diameter of the Earth, which would make it about 100,000 miles in length. I think that's right. I will go check that again afterwards, but I think
so.
Yeah.
So I remember reading somewhere that it's now shrunk and it's down to the size of 2 Earths.
Yeah. So well, the centre of it, certainly, the red bit is definitely much smaller than it was when I was looking at it, 20, 30 years ago.
Oh, yeah.
One other last planet we might just be able to see this month, and this month only, soon be gone, is Venus. So if you're an early riser, you can still see Venus just in the late morning sky. So you'll see it just before the sun comes up. And that really is it for the planets. We don't have any Mercury. We don't have any Mars. And Uranus and Neptune we're going to talk about next month.
Yeah, because you can't see them with the naked eye. Certainly not easily.
Yeah. So those planets and constellations and all those coloured stars we've talked about today can be seen on our monthly star chart, which you will find on our Forest FM Facebook fan page, as well as online at Fordingbridge Astronomers, Wessex Astronomical Society. And it shows the stars around mid-month, around 10 o'clock. So you can print that out if you want and take it into the field with you at night and use it to find the stars. But if you're interested in finding more about astronomy, what to do, Steve?
Oh, you come to one of our club meetings.
You do.
There's 3 pretty active astronomy clubs in the area.
Yep.
So the first one is Fordingbridge Astronomers, and that meets every third Wednesday of the month at the Elm Tree in Hightown in Ringwood. We meet in the barn, so there's entrance directly from the car park for people who don't like wading through pubs.
Yep, good point. Wessex Astronomical Society, our second club, meets at the Allendale Centre in Wimborne on the first Tuesday of every month. Plenty of parking down there too, as there is at the Elm Tree.
Yep.
So come along there.
Cranbourne Chase Astronomy Club meet in Shaftesbury at the Grosvenor Arms.
Super place.
It really is. They meet on the second Wednesday of the month. So,
yeah, and all these clubs, all of us, we welcome new members, all growing very quickly. We love to welcome new people, and maybe it was COVID that did it, Steve, I don't know, but there's been a boom in astronomical club membership of late, and we've had lots of novices come along. If you have even the slightest interest in astronomy, do come along. There's lots of people with similar thoughts and ideas to you. You don't need a big telescope. You don't need even binoculars. You just need a thirst for knowledge and at least one human eye, and we'll take it from there.
Yeah, that does it. In many ways, it's a simple scientific hobby to get into, but it's also, you can take it much, much deeper if you want to.
Yeah. Very fulfilling. Thanks very much for listening today. We'll see you again next month, which will be Christmas. I think we're going to be talking about the Star of Bethlehem. You know, we haven't done that before. Shall we do that? Steve, what do you think?
We certainly could do that. Yeah. I have my theory about that one.
I knew he would have. You know. Anyway, so it's goodbye from me, Mark Hardacre.
And from me, Steve Tonkin.
And as usual,
clear skies.